We're going to solve a differential equation involving a step function. And we have just a normal differential equation, and we have this step function on the right-hand side. Our initial conditions are both zero. That means if this is a spring mass problem, then the spring mass is starting at equilibrium and starting with zero velocity, it would just stay there, right? Like it doesn't have any reason to be moving at all. It's at equilibrium. So that would be our solution, is just y equals zero. It's just going to stay at equilibrium because we're not moving it. We're not pulling the spring. We're not giving it any initial velocity at all. But at time pi, we're turning on some forcing. At time pi, some forcing term is kicking in. So we're going to solve this with Laplace transform techniques, and what we should see is something happens at time pi in our solution, right? We should see that something turns on at that time, because at that time, we're hitting our system with some energy, with some forcing. So let's go ahead and take the Laplace transform on both sides. We have s squared capital Y minus s y of 0 minus y prime of 0. That's the Laplace transform of y double prime, plus 4 capital Y, the Laplace transform of 4 times little y. And on the right, the Laplace transform of the step function times the sine function. Now, this is the alternate to line 5 in our table. We've done examples like this already, so I'm not going to spend a lot of time on that here, but what we get is e to the minus pi s times 1 over s squared plus 1. So we've done the Laplace transform of both sides, and we need to solve for capital Y. Actually, we need to put in the initial conditions, but those are both zeros. So we solve for capital Y. We have an s squared plus 4 times capital Y that we're going to divide and put on the other side. So e to the minus pi s, this is 1 over s squared plus 1 times s squared plus 4. So this is often how we end up with partial fraction situations, is because whatever we had on the left gets divided, and now we've got a couple of terms in the same quotient, and we have to use partial fractions to split those up. I am going to do that and show you the result. We've done a lot of partial fractions in class. We'll be doing more with every homework problem. I'm not going to spend the time in this video to show you the partial fraction decomposition. I'm going to show you the result. We get 1/3 over s squared plus 1 minus 1/3 over s squared plus 4. And that's just how the partial fractions work out in this case. I'm going to rewrite that to make it more table friendly. Let's take the 1/3 out. And this is now going to look like 1 over s squared plus 1 minus, now I'd have a 1 over s squared plus 4. This is not quite ready for our table, right? In the table, if we have a k squared in the denominator, we need a k to go with it in the numerator. So with that 4, I need a 2, and so the trick, of course, is to multiply and divide by 2, and that is our capital Y. We are now ready to write the inverse, and the inverse, do I have room to write the inverse down here? Let's try it. Y, little y of t is, so the exponential, well, let me put the 1/3, I guess. The exponential is going to come in as a step function. So u of t minus pi. And then I'm multiplying that by the inverse of these. So I have the inverse of 1 over s squared plus 1 is just the sine of t. Now, remember, when we have the exponential times the function, the exponential becomes the step function, and when we do the inverse, we have to replace t with t minus pi. So sine of t minus pi instead of just sine of t. And then we have this minus 1/2. And then when we have the 2 over s squared plus 4, the inverse of that is sine of 2t. So I write sine of 2t. But again, I'm replacing t with t minus pi. So it's sine of 2t minus pi. And that is our inverse Laplace transform. And that is our solution of our differential equation. So here's our ODE. We have the solution now. We said nothing should happen until time pi when this forcing term kicks in, because initially it's at rest and at equilibrium. And that's exactly what we have in our solution. Nothing happens until t equals pi, at which point this solution kicks in. And now we have motion according to these sine functions, starting at t equals pi.